everyone. We're group 17. So today we're going to be you guys a presentation about integer linear programming by using both Python and R program. So for the question number one, the first thing we're going to do is to download the Sci-Fi optimization package, and then we import the linear programming into this problem. So the first constraint objective function, the OBG is our objective function. So that's one, all right. And then we have a left-hand side inequality constraint. For the left hand side, we can see a machine A, B, and C. And then for the right hand side, so the total all of them is about 480. And then we will have the left hand side of the equal function, the equal constraint, the max 1, 2, 3, 4, and 5. And then we have the right hand side, which is the demand. And then we'll have the bound, the B and D bound is for the every variable. So we know that's greater than 0. And then we have the option functions for the linear programming, and then we print. So for the bottom we can see for the fun the function one, it, yes, the function one is our optimum result. And then for the success is we found the optimization problem, we found the solution. And then for the X array is the total amount that we should produce. So this is for the question number one by using SciFi to solve this problem. And then we also use the pop, which is another method to run this, to try to solve this problem. So first we use pop, we import it, and we use linear programming minimization because this is a minimization problem. And then we build a model. And for the variable, the first thing we need to do is initialize the decision variables. And then this is the same thing. We just want the lower boundary is 0. And also this is an integer problem. So we want the category to become integer. And then the model is the same thing. The model one is our objective function, which is kind of the same thing. And then we add some constraint to this model. So the first three constraint is about the machine A, B, and C constraint. And then the next 5 constraint is about the mask demand, which is for masks 1, 2, 3, 4, and 5. And then we solve this problem, solve this model. So we print out the result, and then we will try to run this model to see the result. So for the result, we can see for the first, the objective, which is our minimization problem, which is our result. And then for each variable, we can see how much should it produce in this problem. Yeah, and basically this is it for the first problem by using pop to solve this one. And then also we're going to look ICE 4 question number 2. Yes, for this problem, we use pop to solve this one. So kind of the same thing, we just import all of the variables, and then we make it equal to integer. But in this case, we have some binary variables for our constraints. And then we have our model, which is same thing as the ICE in the Word document. And then we'll add some company 1, 2, 3 demand constraints to the constraint of the model. And then also we need to create the supply constraint. And then we have some side constraints for company 1, company 2, and company 3. And that's it for the constraint side. And then we solve the problem by using the same thing. And then we try to run and see the result. As for this one, we have, so this is also a minimization problem. So we will have the objective value, which is 155,750. This is our minimization. And then we will have the each variable, how much should it produce? For example, like x13 means company 1 should produce how many, and the company how many products of number 3. And then we will have the same thing for company 3 and company 2. And that's it. And then let my teammate Ray to introduce question number 3 to you guys. Thank you.
Okay, so in number 3, I'm using R and using LP solve here. You can see the profit matrix here, which is the same as the Excel here, the matrix here. And by using LP solve, we have a 4x4 matrix, which means we have a 16 variables that is down by here. And we need to input all 16 variables like this table here. And by using the equal sign here, giving the constraints, we can solve that. The objective function gives us the optimal value of 29, and I can restart and rerun it again, and we'll show that the objective function here is 29. And we can see all the decision variables here in the solution. And that's it for number 3. And with using R, that's pretty simple. Let's go back to Python and let's solve number 4 with Lu Zhou.
Hi, I'm Joe, and I'll be covering part 4 of our program, and I'll start sharing my screen. Now, everyone can see on the right-hand side is my terminal, and on the left-hand side is our code. So what I did about the part 4 is first to initialize this linear programming problem, and then for the constraint parts, I applied some of our constraints right into this section of our code when I initialized the variables. So you can see that the low bound for level 1 is 0, and the up bound for level 1 is 100. And so it is with level 2 and level 3. So some part of our constraints are already applied to the different levels of our variables. And then these are the binary indicators telling that if we're going to produce on level 1 or not, if we're going to produce on level 2 or not, and if we're going to produce on level 3 or not. And the profits for the relevant level of production is $10, $11, and $12. So for our objective function, this is our objective function, which is the same as the solution on our in-class exercise solution. And then we also add one constraint, which is produce 1 plus produce 2 plus produce 3 equals to 1, which indicates that we'll only have one binary result as 1, and the other two will be 0 in our solution. And then we solve this problem. Because of our objective function as this, we cannot calculate the precise result of our maximized profit. So we applied another function here called integrate profit, which loops through our answers, loops through our levels, produces, and profits. And then if the binary indicator is equals to 1, which means that, oh, we are actually producing in that level, the sum will be updated, and the produce indicator is equal to 1.0, which means we're gonna produce on this level of output, and we will update the sum of our maximized profit. So in the end, our program will look like this. So the optimal solution found is 9200, which is because of our objective function looks like this. And then we use, so for each level of production, we will only be producing on level 3, which is 1.0 of level 3, and then the total amount is 500, and the integrated maximized profit will be 6,000, which is the result from our integrate profit function. And that's our part 4.
Okay, so let's get back to number 5. And with number 5, I'm back to using pulp again in Python. So first of all, we import pulp and import the star, and I also imported the math function. I used the from which is the shipping from as a customers, and named it from 1 to 11. And then I named the facility from Boston to Seattle as dictionaries. Um, and then there's a demand from the bottom view here that we see. And then I also added the fixed costs associated with each plan that's gonna be built. I also added the M value that we're gonna use, which is arbitrary number, arbitrary large number that's gonna use for our constraint. So for each of the facility, I use just 8888, which is a luckier number, I guess. And for the transportation distance, I had to make a dictionary and put all this distance table into my Python here. So in here, I can just call Boston, and then I'll have this 1, 2, 3, 4, 5, and then all until 11, which 11 indicates Seattle. That's the distance from Boston to Seattle here. And then I'll set the problem variables, which is using the facility locations and also using the from which surface transportation to which facility. So let's set the objective function to minimize the cost. In here, I had to use two loops because we have facility and we have a from and to. So I need to use the use variables and the actual cost, which is the fixed cost here of the plant. And I also use the LP sum, which is the linear factor summation. So I also have to loop that through facility and also in customers again. And I also do the constraints for demand and the maximum and use far part here. So let's go down to solve. I use the tolerance of 0.001 just to indicate that if I have a 1 in the variable, it will show up as using this facility in the end. So unit cost here is 60, and then here will be our total cost of production dollars. Let's run this. So our cost of production in dollars is 6366640, which matches our solution here. And we're using locations in Chicago, Dallas, Denver, Los Angeles, Miami, New York, Phoenix, Pittsburgh, and Seattle. So we're just missing Boston and San Francisco, which is correct here. Let's go on to number 2. So we're having 2 more constraints on California emissions. And so I added 2 constraints here. Actually, I added 1 variable called facilities, which is in Los Angeles and San Francisco. Everything else is the same, except that in here, if we are using the California facilities, we have to make sure that if they're going over 20,000 units in that facility, we have to add the fixed cost in. So here our objective function changes. I didn't go through the trouble of using loops since there are only 2 facilities here. So I just added Los Angeles and San Francisco here. And also I have to make 2 more constraints, which is for the Los Angeles and San Francisco, and that is looping through all the facilities and our for the units produced, it cannot go over 20,000, or else it will change the binary variable to 1, which makes the which makes the problem not taking that solution as a location of a production. So let's run this solution again. So in 5B, we have a different network. Here we have, compared to our Excel, we don't have network building in Boston. We don't have Los Angeles anymore, but we have a San Francisco. So we don't have Boston, we don't have LA, but we have San Francisco here. And our cost of production here is this, which matches our answer here in Excel. And so in C, instead of using just the California facilities, we had to do emissions on all of the cities. And that's why I have the emissions here and just have this list of facilities here. And everything else is the same, except that for the California, I added the constraint by having just using LA and San Francisco. In here, I had to use a loop. So I loop through all the facilities here and make sure that they do not produce exceeding 20,000 here. And also the same for our objective function. So I used another LP sum and I used a K here for the emission, and that basically just loops through all the facilities in order. And we can check the solution here by running here again. So that the network should change. So we are establishing not in Boston. It's easier to say the one's not established, and we're not established one in LA. So we're not going from Boston and LA, and all the transported ones are listed here, and we'll skip that and go down to the cost of production in dollars, which is the same as the number given in Excel. Okay, let's go to 5D. 5D is actually a bit easier because we don't have the emission constraints anymore. And all we are doing is by changing the number of production cost to from 60 to 61. And that doesn't change our network solution, as you can see here for 5A. So the network is still missing Boston and not building one from the San Francisco one. And the cost of production in dollars will actually increase by a little bit. So it's 43 million, I guess. So, well, they match the same as the one in Excel. So in this Python, I use a lot of functions, including dictionary, list, OP sum, and for loops. There's double for loops here, and tolerance here for checking the variables here. So that concludes our final project using Python and R. And thank you for listening.